Hello, good morning. I hope you are comfortable by now with 2-point boundary value problems, and we have discussed finite difference methods and how to solve 2-point boundary value problems using finite difference methods. Okay. So, but there are certain other methods for 2-point boundary value problems. You see, we started with initial value problems and then we have come to boundary value problems. So, now having the knowledge of initial value problems, so can we use it to solve boundary value problems as well. Okay. So, this is slightly a different technique compared to finite difference methods called shooting method. Okay. So, as the word suggests, sometimes to reach the target, sometimes we may undershoot and sometimes we may overshoot, in the sense we may reach above the target, sometimes below the target. So, the main idea here is with what angle we should fire, so that we reach the target. This is kind of intuition. Okay. So, let us start discussing shooting method. Shooting methods for boundary value problems. Okay. So, let us start with some physics. For example, when we have autonomous systems, say dx by dt equals to some f of x y t and dy by dt is g of x y t. So, this is called autonomous system. For example, the book by G. F. Simmons on ODE discusses about this. Okay. So, accordingly we must have x of some initial condition, t naught is x naught, y of t naught is y naught. So, that means we are looking for x of t, y of t at any given time. So, this is our solution, right. So, now what shooting method does? So, we are trying to solve for, so this is our, let us say, target. Okay. So, then what is the corresponding initial angle, okay, so that we hit the target. Okay. So, let us switch over to boundary value problems. Okay. So, in the context of boundary value problem, okay. So, in the context of boundary value problem, shooting. So, we have say y double dash plus y dash y is r of x. Then we have the boundary conditions. Okay. So, now what we are trying to do is convert. So, this is a BVP. Okay. So, now we know how to solve IVP. Okay. So, can we convert star, okay, convert star as a initial value problem. Okay. Yes, it is possible. Okay. How do we supply initial condition? Why we have to supply initial condition on y dash? Because already we have y of a, right. So, if you supply initial condition y dash, then this boundary value problem can be converted to initial value problem. So, how do you, so y double plus p y prime q y is r and y of a is gamma 1 and y dash of a is some alpha. So, now this is our IVP. Okay. So, now what is our idea? Suppose if we solve, we can get the solution at any grid point. Okay. So, what is the idea? The idea is solve IVP to get the solution at the boundary point y of b. Okay. So, now what may happen? So, we know the curve, let us assume the end points. So, this is y of a, this is y of b. Okay. Now, we have started with some y dash of a equals to alpha. Let us say with this we hit here, that means something we traced and then we reach here. So, that means this is y at b with alpha. Suppose we slightly adjust the slope, suppose next time we reach here. Okay. So, this is y of at b and let us say here it is y dash of a equals to some delta. So, this is at delta. Okay. So, what is happening? If you adjust your slope, you are tracing a different path, but what is our target? So, this is y of b. Okay. So, this is y of b. So, this is a and this is b. So, this is y of b. So, we need to guess, or rather we need to find out what could be the slope with which if you fire we can reach the target, and how do we reach the target? As close as possible. Okay. As close as possible. Okay. So, that means the problem reduces to finding suitable slope. Okay. So, this is the target. So, is that clear with the shooting method? So, now let us formalize. So, we have so, this is our boundary value problem. Okay. Now, BVP as a system, y dash is z, z dash is r minus p z minus q y, and y of a is gamma 1 and z of we need z of a is y dash of a. Okay. So, we would like to convert BVP as a system, and if we convert we need this missing, okay, z of a. So, this is the slope, right. So, now let us say alpha. So, then we have equivalent IVP. So, we have given BVP, we have converted into equivalent IVP, then IVP can be solved using a favorite method. So, your favorite method say RK method or Taylor series, etc. Okay. So, when we solve okay, so we have a BVP, we converted into equivalent IVP. Okay. However, we have something to do with alpha. So, what we say? We are saying some alpha. Okay. So, we do not know what is this alpha. Okay. So, then once we convert to equivalent IVP, we can x say A, then x 1, x 2, then x n equals to b. Okay. And here we should mention our y of a is gamma 1 and y dash of a is alpha. Okay. So, now if we compute, so we can get the value. Okay. Y of a is given here, y of x 1, of course, with this alpha. So, one can compute y of b with this alpha. Okay. Suppose we change delta. So, that means this corresponds to. Okay. So, now whatever may be the slope one chooses, what is our target? Target is y of b equals gamma 2. Okay. Hence, compare y of b obtained with some alpha minus gamma 2. Okay. We have to compare, right. If is less than epsilon, then we have solved the BVP. Do you get it? See, we have some initial guesses alpha, that is our slope. So, then you solve the IVP using some favorite method, we get the values at every grid point. So, we get the solution at the boundary point as well with the slope chosen. Okay. Now, suppose somebody has solved with alpha as a slope, one of your friends have solved with delta as slope, then we check the difference because our target is gamma 2. So, the difference must be less than epsilon, where epsilon is some pre-assigned. Okay. So, this is the desired accuracy. So, now with some alpha you get let us say up to 10 power minus 2. Okay. That means up to 2 decimals. Suppose your friend with some other, that is let us say delta, gets more, then definitely your friend's solution is more closer to the target. So, what is our aim? See, this is what we are comparing, and the condition we are looking for alpha such that okay. So, this is what we are looking for. Okay. So, that means we need to find solution of, say we define phi of alpha equals to so we are looking for this. That means find the roots of this equation phi of alpha. Okay. So, this we treat it as some nonlinear equation. We know several methods to find the roots of this equation. Okay. So, how do we find the roots of phi alpha equals to 0? Yeah, we can try. We have learnt. Can you name some of the methods? Yeah. So, for example, you have Newton-Raphson method, any other? Yeah, secant method. Okay. So, let us define very popular Newton-Raphson method. Of course, here the prime denotes a derivative with respect to alpha. Okay. But the question is, how do we find the derivative? Okay. So, then let us say we switch over to secant method. So, this is secant method and this is Newton-Raphson method. Okay. So, to solve phi of alpha equal to 0 using secant method, one need two initial approximations, say alpha 0, alpha 1. Okay. So, we need two initial approximations alpha 0, alpha 1. So, then what do we do with this? So, what do we do? We compute phi of alpha n minus 1. Okay. So, when we have these initial approximations, that means these two are two different slopes. Okay. So, the two initial slopes alpha 0, alpha 1 define two IVPs. So, IVP 1 y double plus p y prime q y is r, y of a is gamma 1 and y dash of a is alpha 0, IVP 2 IVP 2. Okay. So, we have two different IVPs. Then what we do? Solve IVP 1 and IVP 2. Solve IVP 1 and IVP 2 to get y at b using alpha 0 and y at b using alpha 1. Okay. So, then when we know this, what will be phi of alpha 0? And phi of alpha 1. Okay. So, that means with this initial slope, if you start, what would be the value at the boundary point? Okay. So, this is what we get. Then how far we are from the actual target, because gamma 2 is our actual target. Then similarly, with this slope, how far we are. So, once we know this, we can compute alpha 2 using secant method. Okay. Using secant method. So, then this will be our new slope, that could be a refinement. So, then when we obtain alpha 2, what do we do? Solve IVP 3 alpha 2, then solve for what? Y of b alpha 2, then check if okay, check if this is less than, if yes, then the BVP is solved. If no, refine alpha via secant method. Okay. So, this is we do it. So, once we get some initial slopes, we start solving the IVPs, then we get the value at the boundary point, then compare with the target. So, let us say they are far away, then we refine. To refine, we use secant method or we can use Newton-Raphson method, but right now we are discussing secant method. So, once you refine, then we get a new slope. Again we have to solve the IVP with the new slope to get the value at the boundary point. So, once you get the value at the boundary point, again you compare with the target, that is the actual value which we are looking for, and check how far we are. Suppose we are slightly close, but we are not so happy, then again we take that value and then refine using secant method, and we do this process until we are happy. That means, until the difference between the actual gamma 2 which we are looking for and the value at the end point which we have obtained via the initial value problem, they differ up to desired accuracy. Okay. So, let us start with a problem shooting method via secant method. Okay. So, example, suppose this is our example, y of 0 is 1 and y of 1 is y of 1 is say half. Okay. Then h is 1/3. Okay. So, now the two IVPs. Okay. So, choose alpha 0 and alpha 1. Okay. Alpha 0 is 1.2 and alpha 1 is 1.5. Okay. So, these are definitely, so these initial choices etcetera may be some from the physical data or some experimental data. So, this is a kind of a guess. Okay. So, that means we define now IVPs, IVP 1, okay. Then IVP 2, so this is IVP 2. Okay. So, then y of 1 let us take 5. Okay. Okay. So, now what we have to do? We have to solve. Okay. Okay. Since for the sake of simplicity, I would like to try just Euler method. Okay. Please excuse me, because Taylor series, RK method, they are little tedious, but you can try with the Taylor series or RK method. Okay. So, we define using Euler method for the IVPs. Okay. So, we reduce to the system, okay. Then IVP 1 y of 0 is 1, then y dash which we have chosen is 1.2. Okay. So, now for this x 0 is 0, okay. So, y n plus 1 is y n plus h, y n prime, that is z n, z n plus 1 is z n plus h 6 y n square minus x n. Okay. So, now using this, let us compute y 1, which is y of 1/3. So, y 0, so y 0 is 1 h and z 0 is 1.2. So, this will be 1.4. Z 1 is z 0 plus h 6 y 0 square. So, z 0 is 1.2 plus 1/3 6 y 0 square. So, that is 6 minus x 0 is 0. So, this will be 3.2. Okay. So, then we proceed further, y 2, this is y 1 plus h z 1. So, this will be and z 2 z 1 h 6 y 1 square minus x 1. So, this I have computed. Okay. So, z 2, then y 3, y 2 z 2. So, we get y 3. So, this is y at 1 using, so this is y at b alpha 0. Okay. Similarly, for IVP 2, okay. So, we have y dashed is z, z dashed is y of 0 is 1, z of 0 is 1.5. So, we can obtain y 1 is same Euler method, y 1 is 1.5, z 1 is 3.5, then y 2 is, you want me to write down. So, y 1 is 1 plus 1 by 3. So, this is 1.5. Z 1 is z 0 plus h 6 y 0 1 minus. So, this will be okay. Then y 2 is y 1 plus h z 1, okay, and z 2 if we compute z 1 1 by 6 y 1 square minus x 1. So, this is okay. Then y 3 is 5.29, and what is this? Y of 1 using 1.5. Okay. So, either of them. So, this is 4.79, and what is our target? So, our target was so assuming either of them is not close enough, then we have to go for secant method. So, y of 1 using 1.2 minus 5 minus 5. So, this is 4.7966 minus 5, and y of 1 using 1.5 minus 5, this was 5.29. Okay. So, assuming both are not less than epsilon, let us say. Now, let us define secant method. So, alpha 2 is alpha 1 minus okay. So, these are essentially our phi of alpha 0 and phi of alpha 1. Okay. So, alpha 1 1.5, then so this will be, so gamma 2 get cancelled, it is essentially y of 1 using 1.5, y of 1 using 1.2 into phi of alpha 1. So, this is y of 1 using 1.5 minus 5. Okay. So, this we have this is 0.3 by this difference. So, the difference of 1 at 1.5, there is 5.29 difference, this one, and this difference we have so this is equals 1 point. So, this is alpha 2. So, having computed alpha 2, what we have to do? Solve z of 0 is alpha 2, which is 1.32. Again Euler method we solve. Let us say on solving we get so I am not giving the details. Y 3 is 4.965. And what is this y 3? Y at 1 using 1.32. And is it close to 5? Depends. Okay. So, you can check. So, mod minus gamma 2. So, this is mod 4. So, this is so suppose you are not happy. So, this is not epsilon because okay. So, then what we do? Compute alpha 3. Okay. So, alpha 3, alpha 2, so this 1.28. So, we are adjusting. Okay. So, then what we do? Solve IVP using z 0 equals to alpha 3 equals to 1.28. Okay. So, then we get, let us say, something like this, then it is not okay, close. So, then we have to again compute alpha 4. Okay. So, we have to continue the process like this, right. So, when we are happy with the desired accuracy, then we say we have reached the slope, approximate slope with which if we fire we reach the target. That means, the entire path has been. So, this is y of b, say we have computed using initial value problems some error. Okay. So, this is computed with some alpha k. Okay. So, this distance is epsilon, right. So, this is a shooting method using secant method. Okay. So, now we have discussed already while shooting method is applied, all that we have to do is we have to refine our slope. So, sometimes you are overshooting, sometimes you are undershooting and all that. So, can we refine slope using any other method? Yeah. So, we have a standard Newton-Raphson method as well. Okay. So, let us look into this using Newton-Raphson method. Okay. So, shooting via Newton-Raphson. So, this is slightly tricky. So, consider y double prime is, so I have considered this type complete nonlinear. So, y dashed of A is alpha. So, this is our alpha. Okay. So, now what is our phi of alpha? Okay. So, now the idea is solve for alpha using NR method. Okay. Now, if you want to define Newton-Raphson method, okay. So, we have to compute. So, the issue is how to compute phi dashed of alpha n. Okay. So, let us phi dashed of alpha equals, see what was our phi? Let us start with phi. Phi of alpha is y of b alpha minus gamma 2. Then if I differentiate with alpha, treating this as two variable function of this argument as well as the parameter. Okay. So, this let us call some eta of alpha b. Okay. Say. Then we have y double is f of x, y of b s or alpha, and y dashed of b alpha. Okay. Differentiate with respect to alpha both sides. See, this prime is x. Okay. Yeah, this is what. Now, if I differentiate with respect to alpha, alpha goes in, I can take, okay, of, so this is eta alpha. Okay. So, this is remember at b. Okay. So, we get eta alpha double. So, prime is I am denoting. Okay. So, this is taken there equals, now right hand side we have to differentiate with the alpha. So, this we use a chain rule, x is independent, dou f by dou y, dou y by dou alpha plus dou f by dou y prime, dou y dou alpha. Okay. Okay. So, please try to understand. So, this is okay, right. So, this is a key definition. So, dou y by dou alpha we are denoting by eta alpha. Then we have this original given ODE that written at b, differentiating both sides with respect to alpha. So, I have shown the working. So, this is the transformation. Okay. So, this reduces to, of differentiating with respect to alpha, left hand side become this and right hand side becomes, using chain rule, this. Okay. Then we have y of a gamma 1. If you differentiate with alpha and right hand side is 0, and we have initial condition. If you differentiate with alpha, this will be, this is not derivative, just to know that it depends on alpha, and right hand side is 1. So, therefore, what did we achieve? We have converted, and one more, this is what? This is eta alpha. Okay. And what about this? This prime can be given to eta, right? How? See, for example, we are looking for, so this will be d by dx of eta alpha. So, that will be prime. Okay. So, with this notation, this becomes eta alpha and eta alpha a is 0, one. Okay. Right. So, what did we achieve? In order to find phi of alpha, we have obtained this. Okay. So, essentially phi dash of alpha, if we solve, see, we are looking for phi dash of alpha in order to use in our Newton-Raphson method. Okay. So, now what did we obtain? So, this is say some on solving T, we obtain eta alpha, okay, which is phi dash of alpha. Okay. Of course, B, right. So, this gives a big tool to compute phi dash of alpha. So, let us see, for example, if y double is y, okay, simplest case we are taking, say y 0 is 1 and y of 1 is 0 is our boundary value problem. Okay. So, now what is our f? Our f was just y. Okay. So, therefore, one is 0. Okay. So, therefore, the IVP for eta, the IVP for eta alpha reduces to, what was our IVP? So, this reduces to dou f by dou y is 1 and this is 0 and boundary conditions. So, we have to find this implies and y dash of 0 is alpha, this implies 1. So, accordingly, the IVP is eta alpha prime is eta alpha 0 okay. So, now how do we solve this? Again system, let eta alpha is some mu, then mu prime is eta alpha. Accordingly, then mu of okay. So, this is our system. So, let h is 1 by 3 okay. So, then we have to define Euler method, of course, equals eta alpha n plus h z n sorry h mu n, then mu n plus 1 mu n plus h eta alpha n okay. So, from this let us solve eta 1. I am dropping alpha because too many suffixes. So, eta 1 is eta 0 plus h mu 0 and mu 1 is mu 0 plus h eta 1 okay. So, that is eta mu 1 is mu 0 plus h eta 0. So, this is 0. So, this is 1. Similarly, eta 2 is eta 1 plus h okay, to mu 1. So, this will be and mu 2 mu 1 h eta 1. So, this will be okay. See, essentially we are solving this using Euler method. Okay. So, ultimately we need a eta 3. So, eta 2 plus h mu 2. So, this will be 9 okay. So, this is our value mu 2 is so this will be Okay. So, we have obtained eta 3. So, this is nothing but phi dashed of alpha, of course, with this b, right. So, therefore, we can obtain phi of alpha n. So, this is alpha n minus y of b at using alpha n minus gamma 2, and this is eta. Okay. So, this is alpha 1. So, let us choose say alpha 0 is 1, and this we have to solve with alpha 0, obtain y at 1 using alpha 0, say this is point, suppose same problem we have to solve. So, if we solve, let us say this is the value. So, this okay, the value we have obtained minus gamma 2. So, gamma 2 was the given gamma 2 was 0, and eta alpha just now we have obtained. So, this is, so we get refined value. Okay. So, this is our alpha 1. Then again we have to obtain. So, let us say this is some 1 point, right. So, we get some value, let us say this is some 0.92, check. So, then obtain y at 1 using alpha 1, again refine to get alpha 2. So, we continue until we get the desired accuracy. Okay. So, shooting method, the idea is same, either we use secant method or we use Newton-Raphson method, the idea remains the same. Time and again we have to solve several initial value problems. For each new slope, we solve the new initial value problem with that slope, and then try to obtain the solution and check how far we are from the target. Then if we are not satisfied, refine your new slope to get a new slope using secant method. Okay. Only difference is, in case of Newton-Raphson, to solve the phi dash of alpha, again we have to solve a system of equations for finding phi dash of alpha. So, that means one set of IVP for the original problem and another set of IVPs for eta, which is our slope, okay, phi dash of alpha. So, this is slightly complicated, otherwise the underlying principle remain the same. Okay. So, with this we have reviewed more or less different methods for 2-point boundary value problems. Okay. So, in the next class we will discuss further more topics related to 2-point boundary value problems and do some problems. Okay. Bye.